Okay, so obviously our Unit 1, the first unit we're going to start with is chemistry in this course. Pretty well most teachers start with chemistry. It's actually, I think, the second or third unit in the textbook, but that's not a big deal. So you can write down, obviously, Unit 1, chemistry. This is going to be its own little note, right, separate from the stuff that we've been doing in the recent past, like safety and all that type of thing. And you can write the definition there. Chemistry is the study of matter, its properties and changes, all right? And there's an animation there, and there was a teacher that was helping us out for a while, and she actually put most of this PowerPoint together and found this really neat animation. I normally wouldn't go that far to find such exciting things, but isn't it awesome? It's exciting, eh? Animation right there. Okay, so moving on here, let's define matter. And I do not need the picture of the balloon and the labels. That's really just to visually kind of help you out. If you want to add that little bit, you can, I suppose, but I don't think it's necessary here. Because also, I'm sure you did classifying matter in grade 9 as well, and so this is really review. So matter is anything that has mass and takes up space. When we say it takes up space, it has a volume. Just a little aside, when it comes to our universe, there really only are a handful of different types of things in the universe. One of them is matter, which is the stuff of the universe. Other things that occupy our universe is light, all right? So light energy and the way light travels, that's a distinctly different thing than matter. Light doesn't have mass. Light travels at the speed of light, all right? Where matter has mass, we can weigh matter, and matter cannot travel at the speed of light. It's one of the fundamental laws of physics, actually. So there's matter, there's light, there's space itself. Space is it's a thing in our universe, all right? Astronomers can actually look at the stars and they can conclude that space of our universe itself is actually growing. Our universe is expanding. So space is actually changing with time. So it's a thing as well, okay? And, you know, if this was 50 years ago, I would stop my list. I'd say you've got matter, you've got light, and you've got space, and that's it. But in recent years, probably maybe the last 10 years or so, there's some really interesting ideas that scientists have proposed. If scientists look at our galaxy, which contains our sun and a whole bunch of other stars, if they look at that galaxy and they look at how it's spinning due to gravity, it's actually spinning too fast for the amount of matter that scientists see. Because as you look out there, you can see stars and you can see the way the stars are moving, so you can kind of figure out their planets. So they can kind of calculate how much mass or matter is in the galaxy. But when they look at the way the galaxy moves, it moves too fast. And so it's like there's some matter that they can't see. There's matter that isn't visible. And they've called this matter that they can't see, they call it dark matter, all right? They simply say that it doesn't interact with light, and therefore we can't see it, but according to our calculations, we predict it's out there. They've never actually seen what dark matter is. They're not sure exactly what it is. There are some ideas that they're really close to experimentally spotting what this dark matter is, but they haven't done that yet. So there's ideas that there may be other types of matter than the matter that we are dealing with here. Our matter, that is, has mass and takes up space, I guess maybe in the future it might need one more addition. It might say it also interacts with light, right? Because light bounces off of matter. That's what allows us to see it. Where this dark matter, light doesn't interact with it, and therefore we can't see it, all right? So there are some other weird things out there that are proposed that, you know, maybe in your lifetime, my lifetime, we'll find out some others. But for now, we've got mass, matter, light, and space, and that's essentially our universe. So we're worried about matter today. And here we've got balloon. It's made of matter. The air inside the balloon is actually matter. It has mass. We can measure it. The string, that's exciting stuff. All right, classifying matter. And this is the classic flow chart that you've seen in the past. Matter at the top of it, and so we'll bring that, classifying matter. We're not going to put matter at the top of it? Well, we've got to put matter at the top of it. So I'm going to do that with my pen. So matter, all matter. My pen isn't working. Excellent. and I'm recording. Do I want to stop this? No, we won't worry about it right now. I'm recording my voice. The problem is the Smartboard program is not activated to turn on the writing feature. It doesn't matter. At the top of that flowchart, put matter. Actually, I'll build the flowchart with you on the board, okay? And you can see there on the side, I got pure substances. What's on the other side? Anybody remember? If it's not a pure substance, then what is it? Yep, it's a mixture. So on the other side, we're going to put mixtures. Excuse me. Now at this point, the flowchart breaks down into subgroups, and then in subsequent slides, we define pure substances. Instead of making extra notes, I'm going to jump ahead to the pure substances slide, and I want you to write the definition underneath here in your nice tiniest little writing. So I'm going to jump ahead here. Don't mind the rest of this. We'll come back to it. I want you to write down here, under pure substances, those 2 bullets, just the 2 bullets, the first 2 bullets. Okay, because I think it's a little overkill to write another complete slide about pure substances. So just write the first 2 bullets under your pure substances. So they contain a single defining particle. We're talking about atoms and molecules here. So we can talk about a pure substance like iron, in this example here. In a hunk of iron, all of the atoms are the same. They're all iron atoms, as found on the periodic table, all right? So that's the pure substances, because the particle that makes it up, all those particles are identical. They're the same, all right? Another type of pure substance we can have is like oxygen gas. Oxygen gas, like many of the gases on our periodic table, are made up of 2 particles put together, and therefore oxygen gas is O2. Now, I don't want you to write all this stuff down. This is online. It's a representation pictorially. I think this is review. We've seen this in the past. I just want to review it. So oxygen gas is a pure substance made up of the same little O2 molecules, all right? And then here we can also have a compound, right, like sodium chloride, like salt, which is made up of a sodium atom and a chloride atom put together. But within salt, all of these sodium chloride units are exactly the same, all right? Okay? So these are all pure substances. They have a fixed composition. That means no matter where I take my sample of iron, it doesn't matter whether I get my oxygen at the top of the tank or the bottom of the tank. No matter where I get that sample, it will all be pure oxygen. All right? There won't be anything else in there. So its composition is constant. Okay? Another bullet that's not here that's really quite important about pure substances, and you don't have to write it down, this is something you'll use in the future, is that pure substances have distinct and non-varying properties as well. And we're kind of jumping ahead here because we're going to later on talk about physical and chemical properties. But the physical properties of pure substances are very well defined. An example, water. When you freeze water, it always freezes at exactly 0 degrees Celsius. And when you boil water, it always boils at 100 degrees Celsius. If you had a mixture, if you put something in that water, like the salt, and you made it a mixture, like salt water, its boiling points and its melting points change. It becomes completely different. So pure substances also have very distinct properties that can be used to identify them, all right? Density is a very distinct property of a pure substance. Boiling point, melting point, those are all very important identifying properties of pure substances. Okay. So on this side, you've got mixtures, right? So I want to jump ahead, and underneath the mixtures part of your flowchart, write those 2 bullets. So mixtures are made up of two or more pure substances mixed together. And there's the graphic representation here. We've got a whole bunch of different looking particles mixed together, obviously, as a mixture. If you could look down on the level that we're looking at. They have a variable composition. Let me just show you a couple of examples of pure substances in a mixture, and I'll be showing you some reactions of these in a moment too. So right here I have a container of sodium bicarbonate. What's sodium bicarbonate also known as? Common name for sodium bicarbonate. Any ideas? Yep. Baking soda. This is baking soda. So if you had a box of baking soda, it'd be just like this, sodium bicarbonate. Actually, it's much cheaper if I go to the grocery store and buy a box of baking soda and dump it in this container than actually ordering technical baking soda, so I do it that way. So this is coming from baking soda. All right. Now, baking soda, in this case, in this form, and you've all seen baking soda. We've got a white powder here. We'll put some on there. And baking soda is made up of sodium atoms, carbon atoms, and oxygen atoms. NaHCO3. I'm losing my mind here. Sodium bicarbonate. NaHCO3. It's got some hydrogen in it as well. So there's all kinds of different atoms in there, but every sodium bicarbonate molecule, it's actually an ion, but every sodium bicarbonate molecule in this sample is exactly the same. So even though it's made up of lots of different atoms, just like water or sodium chloride, this is a pure substance. They're all the same. They're all sodium bicarbonate molecules. Here I've got some vinegar. In the end, we're going to do a sodium bicarbonate vinegar reaction if you've seen it before, but right now I'm not going to do that. Let's just talk about the substances. This is vinegar, and we'll put some in here. It's not that exciting. It's colorless. It's transparent. And this is a mixture. Vinegar is a mixture of two molecules put together. Does anybody know what the two molecules are? I'd be really impressed. Water is one of it. It's mostly water. And the other molecule is called acetic acid. All right, so it's a mixture of acetic acid in water. And this particular vinegar is made up of 5% acetic acid put in water. So if I had 100 milliliters of vinegar, I'd have 5 milliliters of acetic acid and 95 milliliters of water. But you can buy vinegar that's different strength than this. In other words, I can buy a vinegar, a mixture, that has a different composition than this vinegar. If you were to buy pickling vinegar, it can have up to 12% acetic acid. So in 100 milliliters of the vinegar, you'd have 12 milliliters of acetic acid, which makes it a different mixture. It's got the same components in it, but its composition is different. And if I were to add water to this vinegar, I would be changing its composition from anywhere from 5% down to, well, it depends on how much water I add, right? I could dilute it down to a very low percentage. So mixtures have variable composition. You can change that composition, okay? Now, along with my statement about pure substances having a nice definite melting point and boiling point, mixtures do not. An example of a mixture, butter. Butter is a mixture of, I really don't know, biological product from milk. It's got to have some milk fat in there somewhere, and I don't know. I have no idea what else is in there. It's a mixture of stuff. It's all kinds of stuff. Butter does not have a definite melting point. When you take butter out of the refrigerator, it doesn't just, bam, melt on you all of a sudden. You know what I mean? If you were to get it to the right temperature, boom, oh, it's all liquid all of a sudden. What happens to butter as you take it out of the refrigerator and you heat it up? If you were to heat it up very slowly, what happens to it? Yep, it gets soft. So it doesn't have a definite melting point. It kind of gets soft, and eventually, after many degrees of heating, it eventually melts. A pure substance like water doesn't work that way. You get it to 0 degrees Celsius, bang, it melts. The temperature of that melting ice is 0. The temperature of the water that's coming off of it is 0, and once it's done melting, then you can warm up the water, right? So pure substances have definite melting points, boiling points, where mixtures do not. All right? You try to put vinegar in a freezer, and you end up with a slushy scenario, not a nice ice cube, because the mixing molecules prevent nice freezing. All right, so that's another effect. Okay, let's now go back to our properties. So we're at this point, and let's now look at the element side of it. So elements are made up of one type of atom. If I'm giving you a question on, I give you a bunch of stuff and I say, tell me which ones are elements and which ones are blah, blah, blah. What's an easy way to tell if it's an element? There's a place you can go and check. Yep. Yeah, go ahead. What do we got? Megan and Megan. We'll go with Megan number 1. The periodic table. The periodic table is loaded with the elements, right? So you could always go to the periodic table and check it. So we're talking carbon and nitrogen and oxygen, right? Even though, and you may have learned this, did you guys learn about the Hofbrinkel gases? Yes? Yeah, Mr. Williams loves the Hofbrinkel gases. That's good stuff. I have some issues with the Hofbrinkel, using a clown with balloons to represent gases that have two atoms stuck together, but still, I'll tell you later why I have issues with it. But even though we've got O2, it's still an element, right? So it's a molecule with the same atoms, one type of atom. Compounds contain 2 or more elements in a fixed proportion. All right, I'll tell you why I have a problem with the Hofbrinkel picture. What is it? There's hydrogen, and then there's nitrogen, and oxygen, and fluorine, and chlorine, and bromine, right? If it's vaporized, and iodine, I believe, I2, correct? Yes, is that what they are on the little clown? It is, trust me, it is. Those are the Hofbrinkel gases. Here's my issue with it. Hydrogen is lighter than air, so it will float like helium. Nitrogen is about the same mass as air, so it shouldn't be floating. It should kind of be hanging kind of, beside the clown. Oxygen is heavier than air. Fluorine is, fluorine's a dangerous gas. I don't even know what its density is. Chlorine's heavier than air. Bromine is. The rest of those balloons should be on the ground, instead of just floating up there. That's a poor representation of those gases.
You could just draw the balloons on the ground.
So you want me to redo the Hofbrinkel clown and redo it with correct balloon positions? Maybe I could. I'm not an artist. All right. Sodium chloride, water, sodium bicarbonate. All right. The acetic acid molecule, that's a compound. We have pure acetic acid in the chemical storage room. It's a little dangerous. It's quite strong. It really stinks, right? If you think vinegar has an odor to it, pure acetic acid really has an odor to it. Those are all compounds. Mixtures. Homogeneous mixtures. The parts of the mixture, and that's what we mean by parts, those different things, cannot be seen individually. Homogeneous. In the grade 11 chemistry, if you take it, and because I teach the grade 11 chemistry, you can have a little preview of it. We have a term for a homogeneous mixture where you cannot see the individual parts. We say that it contains one phase, all right? Now, you don't have to write that down. You don't need to use those terms. If you'd like to, you could. But we say that it has one phase. This is a mixture of vinegar and water, and if I look at that, I cannot see the individual water and the individual vinegar. And so, in other words, we say that it has one phase. A phase is when something has a distinguishable boundary. In other words, you can see the edges of it. That's what we mean by they cannot be seen individually, right? Let's write down the heterogeneous, and I'll give you some examples of something where you've seen different phases and the distinguishable boundaries. So in heterogeneous, you can see the individual parts. Look at here, pizza. That's a grade 9 and it's grade 10, grade 9 and 10 way to talk about heterogeneous mixture. Pizza, you can see the mushrooms and you can see the cheese. We don't, in chemistry, we don't do a lot of experiments on pizza. So it is a good example, but it's silly. Oil and water, that's a good example. You could draw this underneath if you'd like. So if I had a graduated cylinder, it doesn't have to be that big, I'm just drawing it quite large, and I did have some water, maybe even some vinegar, and I put some oil in it, maybe I'm making some salad dressing or something, and I shake it up, then you've probably seen before that there's droplets of oil that kind of float around in the water for a while, and then in the end the oil ends up at the top, right? Well, you can see those droplets of oil, and we would describe the water as being the water phase. We would say that that's the part of the mixture that's in the water phase or the aqueous phase. And then the oils of droplets, that would be an oil phase. And because I can see the edges of the oil droplets, I can see the different substances, and therefore we say it's heterogeneous because there's more than one phase in the mixture. That's the term we use in grade 11, right? If homogeneous, and I just had my acetic acid, I'm not going to do acetic acid in this case, I'm just going to put in here water and NaCl, some salt. You can't see the individual NaCl. In other words, that's just one phase. I can only see one boundary, the boundary around the glass. That's a homogeneous mixture. There's only one phase, right? Our air in front of us is a mixture. It's a mixture of nitrogen gas, oxygen gas, there's some carbon dioxide, some water vapor, some argon. But you cannot see those individual things. So our air is a homogeneous mixture of gases. If we include ourselves within the air, I can see the edges of you. That's how I locate you in the room. I can see the desks. So us in the air is a heterogeneous mixture of people phase and air phase or something like that. You see the idea? So that would make it a heterogeneous mixture. It depends on what you're talking about. Okay? So that's how you differentiate between the two. All right, excellent. And there's matter at the top, finally at the very end. What a silly thing. We talked about the pure substances. We can now say that these are elements and compounds, but that's not a big deal. We've talked about mixtures. Can't really tell whether this is heterogeneous or homogeneous because I'm not really, indicating whether I'm talking about on the molecular scale or maybe on a large scale, right? If this was on a molecular scale and you couldn't see those particles like in a solution, then it might be homogeneous. Or if this is actually a box full of different rocks or something, it would be heterogeneous, right? So we won't stress about that. Classify the following. This is classically what we do with you guys in the grade 10. It's always fun. I don't think this is something we need to write down, but let's go through it. Sulfur. What do you think? Oh, it's already down. Sulfur. What is it? Pure substance or mixture? Yep, Megan, number 2. Pure substance, excellent. And is it an element or a compound? Yeah, it's an element. It's on the periodic table. Excellent. Orange juice. I hate the orange juice example. I absolutely hate it. This is I didn't make this note. I would have taken orange juice off. What's that? Yeah, you see? That's why I hate the orange juice question. Because we've got to have a pulp discussion. And the pulp discussion never goes well. I bring home pulp juice and Jared loses his mind. I hate pulp. That's my son, by the way, and I'm recording this. I really don't care. He's going to be mad at me. It's going to be fun. Jared just loses his mind. I hate pulp. And then my daughter, I like pulp. Oh, it's crazy. So is it heterogeneous? I'm giving it up. It's a mixture. It's a mixture, right? But then somebody says, oh, it's homogeneous, right? And then somebody says, well, does it have pulp in it? Let's forget about the orange juice. Chlorine, what is it? Yes, sir. Pure substance and element or compound? Yeah, nice job. Helium. Yep. Yeah, very good. Carbon dioxide. Yep. Yeah, very good. Salt water. Yep. And what type? Yeah, homogeneous. That's actually a little bit of a trick question. If it's completely dissolved, it's homogeneous. But if I dumped so much salt in it that it couldn't dissolve anymore, because you could do that, you could pour so much salt that it can't dissolve anymore, and you end up with a little pile of salt on the bottom. At that point, it would become heterogeneous, because you can see the salt on the bottom. But a solution of salt water, you'd be correct. Distilled water, which means do you know what distillation means? Anybody know what distillation means? What's that? You boil it and let it evaporate and catch what's evaporated. And when you boil it, you only boil the water off. So when you boil it and catch the water vapor and turn that into droplets in the liquid, it's pure. It becomes pure water. So distilled water is pure. It's a pure substance. It's a compound. Potassium. I don't have names yet, so there's a whole lot of hey you, but anyway, I got Megan 1 and Megan 2. Yeah, Marissa? Yeah, very good. Laundry detergent? What does that have to do with chemistry? Laundry detergent. I'd have to think. All right, I got it. Yep. Yeah, I think it's mixture. Is it homogeneous? It really depends, doesn't it? Again, we're back to pulp here, aren't we? You got the powdered stuff. Is that a mixture? Yes. Is it homogeneous? I don't know. We got the Tide liquid stuff, but it's not very transparent. It almost looks cloudy, which means you can almost see those little particles in there. You know what I mean? Laundry detergent. A copper nail. It's made of copper. Yeah, and it's an element. It's on the periodic table. Excellent. Good. Hopefully I haven't... Oh, and here's another example. Here we go. So this is if we're on the molecular scale. So now we're doing this as if we're on a molecular scale. What's this one? Yeah, mixture, pure substance, pure substance. Yeah, it's a pure substance. All the particles are the same. No need to write that down, is there? We're getting this? Let me know if I'm moving things too fast here. Okay, so that's our classification of matter, but I do want to continue on and talk about now properties. So we're going to go up to the top here, and you can put a new title on this. You don't need a new date on it. It's the same date. Again, I haven't taught the grade 9 in a long time, but I'm pretty sure you discussed these things in grade 9, right? Let me know. Give me some nods here. Yes, no? No, did you take grade 9? Were you pay attention in grade 9? Oh, okay. So did you talk about that? All right, good. Give me a blank stare. I thought maybe it was like, I don't know. So now we just want to talk about properties. Again, we're talking about physical and chemical properties. That's really what we want to get to for the end of this. I'm looking at my time, and it should work out. I should make it. Don't start writing these slides until I tell you, because some of them, like I say, they're just kind of examples and filler, and that does not serve you any purpose in your thing. Like this, it says review. Now, I'm quite sure that when we designed these PowerPoints that we did one on the one day, and then we must have did something else on the next day. So chemistry is the study of matter and its properties and its changes. Matter is anything that has mass and occupies space. We already know that. Don't write this down. All matter has physical and chemical properties, and that's important. So let's now write this down, and let's define these things, physical properties. But don't write down the last bullet. And I do want you to add here, and I wish my pen was working. In the third bullet, at the end, I want you to put density, right? The density. It's another important one. I should have paused my movie and taken the time to allow me to write on the smartboard, but that's okay. So in that third bullet there, it's right there. Not that it's, the most important property, but it is an important property. Characteristic or a description to help identify matter. And yeah, no, that's good. The state, solid, liquid, or gas, color, odor, luster, solubility, melting point, boiling point, density. There's all kinds of others, but these are good to start with. I don't necessarily want you to write the last bullet. If you wrote it, it's not a problem. Quantitative or qualitative property. What does quantitative mean? If a property is quantitative, what does that mean? Yep. With numbers and stuff. Excellent. With numbers and stuff. Yeah, yes. I'm trying to get you to use your words. Any property that we can measure and represent with numbers and stuff. Yeah, maybe units is what you want to put with that. Numbers and units. Yeah, numbers and stuff. That's all right. Now, chemical properties can be quantitative as well. We can quantify chemical reactions in certain ways, and that's why I didn't necessarily want you to put this with just physical properties, because we can quantify chemical properties as well. What's a qualitative property? Yep. Oh, you can't use quality in the description of qualitative. Like the quality and stuff? It's the quality and stuff. You're right, it's quality, but let's see if we can define it without using the word quality. I've stymied everyone. You're stuck on the word quality. Yep. Yeah, you can. It's something that you can see or sense, right? So maybe that you can sense with your hands. Can you see quantitative? I guess you can't. You got to use a ruler or a measuring device to get the quantitative. Yeah, that's not a bad start. It's not a bad start. So we can use our senses. It usually just involves a description of what we sense, right? So it's a description using words of what we sense as opposed to numerical representation of a value, all right? Okay, good stuff. Don't write this down. Again, examples. Physical properties of a ripe apple. Qualitative properties. Do we want to write this down? Do we want to write this down? We don't want to write this down, do we? No. Physical properties of a ripe apple. The color is red, it's smooth to the touch, it smells sweet. Quantitative properties, weighs 200 grams, 5 centimeters tall. I've never really measured the height of my apples. Oh, you're tall for an apple. Whoa, a little weird. All right, chemical properties. Refers to a possible change of a substance into a new substance. Really, in a moment, I'm going to talk about physical changes and chemical changes. And really, students struggle, and I don't struggle with it, but I find that really a chemical property is really the same as a chemical change. The chemical property is just kind of describing what could or is going to happen when the chemical change happens. So it's describing the possible chemical change, right? So if you're going to describe a chemical property, you really need to know its possible chemical changes that it can undergo, all right? So you need to have a knowledge of the chemistry of the substance in order to describe its chemical properties. That's more difficult. Physical properties are easy. You take a look at it. It's red, right? It's 5 centimeters tall, right? You don't have to know about what possible chemical reactions it can do. But in order to know a chemical property, you need to know its chemistry, all right? So you need to know whether something can be corroded or can combust or that type of stuff. And again, we're not going to write this down. Chemical properties of a rotten apple. The inside of the apple can react with oxygen, and then it can change color and become red and that type of thing. So again, you need to know that. All right, describe the physical properties of. Let's actually go through this. You might think this is kind of, oh man, Mr. Sanders, you're going to make us describe what this stuff looks like. And this actually is a good activity, because when we do labs, when you write your observations and let's say you're looking at a reactant, there are certain ways I want you to describe their physical properties. Because the only way to know if a chemical has actually undergone a chemical change is to compare its physical properties before you try to do a reaction and compare its physical properties after you've done the reaction. So you need to be able to state those physical properties quite clearly. I'm going to switch this over, and I hope this works. I'm going to switch this over to here because I'm hoping, is this going to work here? What I want to do is I want to put the substance, excellent, substance, all right, and here I'm going to put the physical properties, and here I'm going to put the chemical properties, all right? You can write that down. And what was the first one on that slide? I think it might have been baking soda. Is that correct? Let me just do a quick switch back. Baking soda. I'm going to write down sodium bicarbonate. Sodium bicarbonate. I have to say it like that or I spell it wrong. I'm one of these hooked on phonics guys, which usually doesn't serve me very well. Now, how would you describe our sodium bicarbonate? Actually, I'm going to give you a heads up. When we describe a chemical in chemistry, we always use 3 adjectives. And we always describe what its how it interacts with light, number 1 is the first one. So, can light go through it? Is it transparent? Can light partially go through it? Is it translucent? Right? Have you heard of those terms before? Or can light not go through it? Is it opaque? That's number 1. That's the first descriptor you use. Second, its color. All right? And third, its physical state. Now, its physical state can be solid, liquid, or gas. But you can also use terms like powder, which implies solid, right? You can also use things like crystalline solid if you're dealing with like an actual crystal of some sort, to give a little more description. And when I ask you to do observations in your lab reports, I always want those 3 adjectives at least. It's got to have at least those 3 in order to properly describe your substances. So now I ask you the question, our sodium bicarbonate, how does it interact with light? What is its color? And what is its state? How would we describe it? Yep? Yeah, excellent. A white opaque powder. Yes, and actually I want the color first. Very good. It's a white, opaque, powder. Or solid I would have accepted. Okay? Since I've got the vinegar out, let's do that one. I'm not going to say acetic acid solution. I'm going to put here vinegar. You have to say it that way or you spell it wrong. Like vinegar. You need the E in there. That's just me. How would you describe our vinegar? So again, sorry, I want the color first, then how it interacts with light, and then that's the way we do this. So what is this guy? Yep? Yep, a colorless, transparent liquid. Please don't say a clear colorless liquid, because clear and transparent are synonyms. Clear means that the light is able to go through, all right? Oh, I'm making a movie, Mark. Oh, we're going to have a joke in our movie. All right, here we go. 1. Got to have 1. How much fun can you have during arithmetic? Well, you can have some fun. It's good stuff. Thanks. Oh, okay. What do we got? Thank you, sir. Thank you very much. All right. I think one of them was gold. Let's go with gold here. Actually, gold's not a bad example. So, can we imagine it, or do we need to see it? Ooh, there's the gold. Ooh. Now, a very important other thing about writing observations, you should never put a conclusion in an observation. All right. So when you write an observation, if you think something is hot, you shouldn't write down that it's hot, because you haven't tested that it's hot. You know what I mean? If it just looks hot, it could just be red. Right? It could be glowing red. So we don't want you to ever to put conclusions in your observations. Now, sometimes, you know, what color would you describe gold as? Yeah, it's gold, right? And you might think, oh, I'm making a conclusion about the identity of the substance. But we have certain colors that we use in English that happen to come from elements. So if you were to say that it was a gold opaque solid, that would be acceptable. You wouldn't be deducted for making a conclusion that it was gold, right? You could actually have a substance that isn't gold that you describe as a gold, that isn't the actual gold substance, right? That is the gold color, you'd still use gold to describe it, right? So we don't like it when you put conclusions or ideas in your observations. Observations should be the easiest thing in the world because all you're doing is describing what you're seeing very easily. So in this case, gold, opaque, opaque solid. All right, chemical properties. Well, I've chosen vinegar and baking soda for a reason. Does anybody know what happens when you react vinegar with baking soda? Anybody know? What's that? It fizzes. It fizzes. It produces carbon dioxide. It reacts to produce carbon dioxide. It's a double displacement reaction. We'll talk about those things later on when we get to different types of reactions. So a chemical property of sodium bicarbonate reacts with acids to produce CO2. All carbonates will do that. Chalk is calcium carbonate. It'll do that. Vinegar, we could say it reacts with sodium bicarbonate to produce CO2. That's fine. It is corrosive. It will ultimately, could corrode metals, et cetera, et cetera. So I'm just going to put corrosive. Corrosive. Chemical properties of gold. Gold's a very unreactive element. It's one of the most unreactive elements. Oh man, to describe I shouldn't have picked gold. To describe a chemical property of gold, let's just say it's it's not completely unreactive, but it's highly unreactive. We'll put that. Highly unreactive. It won't even react with regular acids. You have to create what's called a superacid by mixing different types of strong acids together to get gold to actually react with an acid. So it's highly unreactive. Anyway, let's take a look at mixing some baking soda and vinegar here. That's good stuff. Let's start by just pouring some on the watch glass and see what it does. Yeah, it's fun. But let's constrict some in a test tube. Let's see if we can get it to do something. Do I plan on making a mess? Do I have anything here that I really care about? No, not so bad. That's just fun. It's good stuff. All right. I was going to show you something else, but we'll get to right into the end. Maybe I'll show it to you at the end. Okay, so we've described some physical and chemical properties. This is just a little bit of a practice thing. Identify the following as chemical or physical. I'm also going to get you to tell me whether it's qualitative or quantitative. Don't need to write this down. Just some practice stuff. The density of copper is 8.94 grams per cubic centimeter. So is this physical or is this chemical? Yep. Physical. Excellent. Is it quantitative or qualitative? Yep. Sorry? Quantitative, correct. Potassium metal reacts violently with water. It's a really cool reaction to see. Yeah, Mackenzie? Sorry? It is a chemical property because it's describing a potential reaction with it. This is qualitative because it just describes it, and the rest of them are qualitative because they don't have any numbers in it. I think you get that idea. Gasoline ignites very easily. Ooh, yep. Chemical, yep. Gold is a soft and lustrous metal, yep. Physical, very good. Sulfur is a yellow powdery solid. In the back. Physical, excellent. Any questions or concerns on physical properties and chemical properties? We don't need to be wasting our time. Chemical change. Oh, yeah, now we got to talk about the changes. Okay, we'll define this. So a physical change is a change of state, size, or form. No rearrangement of the molecules. That's the key. That's the key statement right there. Even though it changes, the molecules remain intact and are still the same molecules that they were at the beginning. If a piece of ice, which is made up of water molecules nicely in a row, melts, it just means the water molecules are now able to move freely in the liquid state. They're still water molecules, all right? So there's no change in the molecules themselves. Dissolving. You take sodium chloride salt, you put it in water. The sodium pieces, they separate out, but they're still the same sodium ion pieces and the same chloride ion pieces. So even though they've dissolved, they're not changed in any way chemically. Sugar dissolving, even though the sugar is now in the water, those sugar molecules are still intact. Freezing, breaking. Breaking is like, if something smashes, then it's still the same chemical, all right? Sometimes term indicate of physical changes. All right. So here we go. Look here. It's a bird. It's a plane. Yes, but it's still paper. That's Miss Weed is the teacher who made these up, and she was kind of a joker, so she put all that stuff in there. But okay, chemical change. A reaction that produces a new chemical substance. So once the chemical property has expressed itself and you've done it, then you've now got a completely new substance, and you can't easily get that substance back. Physical changes, you can get the substance back quite easily. If you melt the ice and turn in the liquid water, you can put that liquid water back in the freezer and get your ice. But a chemical change has a rearrangement of the atoms in the molecules, and therefore you need to do some chemistry, a lot of chemistry, in order to get that substance back. So new molecules are formed, starting with iron, pure iron. As a nail rusts, it ends up becoming iron oxide. Oxygen has been combined with the iron. Fire burns. You can't get the material back that you've combusted because it has been turned into carbon dioxide and water. And I haven't burnt anything yet in this class, have I? I think it's time I burn something. So I'll prepare to burn something. What did I do with my crucible columns yesterday? We'll use my tweezers. 5 indicators of a chemical change. A new gas is formed. A precipitate forms. Do we know what I mean by a precipitate? No? We don't know? Yep. Yeah, when you mix two liquids together that are transparent and are solutions, and you get a solid that is formed that settles to the bottom. So it precipitates out, like precipitation, like when it rains. Precipitation is a precipitate. It's when a liquid is formed in air and it precipitates out. Same type idea, except it's gas to liquid as opposed to liquid to solid. So it means that a new state of matter has been formed and it settles out. Color change. That's pretty self-explanatory. Get a new color. Heat or light is absorbed or released. Typically, we think of it as being released when we burn something. I'm going to burn something in a minute. But heat can be absorbed. If you have ever, hurt an ankle or or an arm or something, in some sport, your trainer may have those little ice pack thingies. Those are two chemicals that are separated. You mix them together. A chemical change happens that absorbs heat and and you put it on your ankle and it absorbs the heat out of your ankle and you feel good. I don't know what you feel, but anyway, that's an example of heat being absorbed. So not only is heat giving off, but it can be absorbed. The reaction is difficult to reverse, so you can't get the stuff back. Let me just take a look at what my next slide is. Some examples, law of conservation of mass. Actually, I will do that note on the law of conservation of mass before I show you some combustion, and then I'll let you work on some problems. So there we've got some examples of some chemical changes. Look, here's gases formed. That's exciting. There's a precipitate formed right there. All right, that new solid would settle out. And here we've cooked our eggs. We've got to put the nice little food analogy in there. Right, if you have a raw egg and you cook it, you can't get the raw egg back easily. That's a chemical change. And that's burning magnesium. What? I was going to burn some magnesium. Oh, well, I'll still burn it. Identify the following as physical or chemical changes. Again, let's not write this down. Glass breaks. Yep, Megan. Physical. It's just smaller pieces of glass, right? Still glass. Magnesium burns with a bright light. Yep. Chemical. Water freezes. Yep. Physical, still water even though it's in the solid state. Rust forms on your car. Yep. Chemical, very good. Peroxide is poured onto your cut. Oh. Yep. Yeah, it is chemical. It bubbles and it kills bacteria and does all kinds of exciting stuff. Okay, last thing before I give you a little bit of homework, and then I will show you some chemical changes. The law of conservation of mass. Again, I'm assuming you talked about this last year. I actually think you may have done an experiment last year on it. Does that sound correct? No? Any physical or chemical change obeys the law of conservation. Of mass. That should say of mass. Any physical chemical change obeys the law of conservation. I guess so. It's of mass. This law states that no mass will be created nor destroyed in any physical or chemical change. You don't have to necessarily, it's not a bad little example. A folded piece of paper still weighs the same as it did when it was unfolded, even though you physically changed its appearance, right? But even a chemical reaction, if I burn something and I were to catch all of the products and weigh those products at the end, they would weigh the same, all right? Years ago when I taught grade 9, we used to do this experiment, and depending on who your teacher was, you may have done it. It involved taking something like an Erlenmeyer flask, bigger than this, and a test tube that could fit in the Erlenmeyer flask. And we would put one chemical in the Erlenmeyer flask, and then we'd put a second chemical that's going to react with it in the test tube, and we'd slide the test tube in very carefully so they didn't mix with each other, right? One liquid's in one container, and we put a rubber stopper on it, and then we would weigh the two things together, and we'd write down the mass. Did you not do this experiment? Do they not do it anymore in grade 9? That's too bad. Actually, it's the most disappointing experiment in your entire science life, because I did this in grade 9, and I was very disappointed at the end, because here's why. First experiment we were ever going to do in science. High school, man, it's the greatest thing ever. We put them in carefully, we weighed it, we wrote down the mass, we left the stopper on, we mixed the chemicals together, they changed colors, oh, it was great. There was a chemical change, and then we put it back on the scale, and what do you think that scale read? Any ideas? If no mass can be created nor destroyed during a chemical change, and I didn't take that stopper off, and when I put it back on the scale, it read the same. The most disappointing result in an experiment in my entire life. I thought the thing was going to weigh 10 times more, it was going to be massive. Doesn't change at all. Doesn't matter. Because during a chemical reaction, the particles just switch around and trade places. They don't leave or they don't come in. So the mass after the chemical reaction is exactly the same as the mass before the chemical reaction. And that's the law of conservation of mass, right? So during a chemical or physical change, the mass of the products are exactly the same as the mass of the reactants. I won't put you through that painful experience like I had, disappointment in science. There's some questions you're going to work on for homework tonight. Just get